discussing about the voltage regulation in alternator. Uh, Actually, this will be discussed in two parts because there are three ways of calculating the voltage regulation. So, one part we'll be discussing today, and the other two parts will be discussed in the next part. And today we'll also discuss the three basic requirements which is there for calculation of the voltage regulation. So that's the reason this has been divided into two parts. So the topics to be covered today are the definition of the voltage regulation, then determination of the voltage regulation, then the three major requirements is measurement of armature resistance, open circuit characteristics and short circuit characteristics. And synchronous impedance method is the first methodology to calculate the voltage regulation. So the voltage regulation of an alternator is defined as the change in the terminal voltage from no load to full load, that is the speed and the field excitation be constant divided by the full voltage. That means the field excitation we are not supposed to vary it, and the speed will be constant so that the frequency of the supply is constant, and therefore it is mathematically we can write it as percentage voltage regulation is equal to no load voltage minus full load voltage divided by the full load voltage, or we can write it as E0 minus V by V into 100. You already know what is A0, V, and the drop E0 minus V has to be calculated for the voltage regulation. In the last phasor diagrams we had drawn this, the terminal voltage and the no load voltage E0. So E0 minus V is the arithmetical difference and not the phasor difference. In case the leading load power factor is there, in case of leading load power factor, the terminal voltage will fall on removing the full load, hence the regulation is negative in that case. And the rise in the voltage when full load is thrown off, it is not the same as the fall in the voltage when full load is applied. So these are the three major things for the voltage regulation, and you can observe this over here in the graph that for unity power factor it is the straight line graph, the variation of the terminal voltage with respect to the load current, because they will be for unity power factor the armature current will be in phase with the terminal voltage, that's the reason. And for lagging power factor it is a drooping characteristics, and while for the leading power factor it will increase initially and later on it will come and drop down. So how do we determine it? Because the kVA rating of commercial alternators are very high, so we can't load it physically, nor it is practicable to determine the voltage regulation by direct loading of the alternators or the synchronous generators. Therefore, there are several indirect methods by which we try to determine the voltage regulation. So these methods require only a small amount of power as compared to the power requirement of for the direct loading, because suppose you have got an alternator of 1000 kVA, you will have to connect a load of 1000 watts so that the voltage regulation can be observed. So that is not practically possible to have a load of that quantity. Therefore, indirectly we try to calculate the voltage regulation. So three such methods are available, that is the synchronous impedance method or known as the EMF method, ampere turn method or the MMF method, and the zero power factor method or the Pottier method, because we draw a Pottier triangle, hence the name is given as Pottier method. For any of the methods to be applied, three things are major requirement, that is the armature resistance, the open circuit characteristics and the short circuit characteristics. So we'll first try to avail this data, or we'll first try to get these data, that is the armature resistance, open circuit characteristics and the short circuit characteristics. So how do we measure the armature resistance? The armature resistance is measured by directly applying DC voltage and measuring the current, and your R will be equal to V by I, so that will give you the RDC. But the AC resistance is higher than the DC value due to the skin effect, and hence the effective resistance becomes 1.5 times the RDC approximately, because there is a range from 1.25 to 1.75. So average you can take it as 1.5 times the RDC. Now this is the circuit which can be used. The armature will be connected in star and the supply will be connected between any of the two windings. Therefore, you can say that RDC is equal to VDC by IDC, but because of this star connection, this two windings are connected in series. So RDC is equal to 2R1. So R1 will be equal to RDC by 2. And then you can calculate the AC resistance, that is 1.5 times the DC resistance. Now the open circuit test. For the open circuit test characteristics, this is the circuit which has to be applied. That is, there is no load connected at the armature of the given circuit. Just we have kept all the three terminals open, and a voltmeter is connected to measure the line voltage between two of the phases, and we try to vary the field by having a rheostat in the series, and the current is used to measure the field current. So when you draw the curve between the field current and the EMF obtained with respect to the field current, you get a curve which is similar to the BH curve, and that is known as the open circuit characteristics of the generator. This is the short circuit characteristics to obtain. For the short circuit characteristics, in all the three phases we have connected an ammeter and is externally shorted, and again we try to vary the input field supply and measure the field current and try to obtain the short circuit current at the rated armature current, that what will be the field current required to make the rated current flow in the on the armature side. So that is the short circuit characteristics. So as you vary the field current, it's a straight line graph for the short circuit characteristics, and this graph will be used for the further calculations. Now what is the SCR? Because this is a common thing which is being used for the rating of the generators. So the short circuit ratio is an important terminology for the synchronous generators. It is the ratio of the field current to produce the rated voltage on open circuit to the field current required to circulate the rated current on short circuit condition while the machine is driven at synchronous speed, is known as the short circuit ratio of a synchronous machine. So we'll just try to have the graph, and this is your graph. Now OCC is the open circuit characteristics and SCC is the short circuit characteristics. To get the actual voltage, the required field will be IF1 under open circuit condition, and IF2 is the field current to make the rated current flow in the given circuit. So the short circuit ratio was to produce the rated voltage under open circuit. So that is IF1. So IF1 divided by IF2, which is the short circuit, this is the field current required to make the rated current flow in the armature circuit. So it will be given by OA divided by OD. OA is the same as OE because it is the isosceles triangle. So AE divided by DC, or you can just make it the similar triangle because this is a straight line graph SCC. So by the similar triangle equation, you can make that OA by OD is equal to AE by DC and ADC is equal to AB. So you can write as SCR is equal to 1 by AB by AE, and AB by AE is nothing but the synchronous reactance. Hence SCR is given by the inverse of the synchronous reactance or the reciprocal of the synchronous reactance of the given machine. So the value of the synchronous depends on the saturated conditions of the machine, whereas SCR is specific and defined at the rated voltage. What is the significance of the SCR? Why do we calculate it? The smaller the value of SCR, the larger will be the synchronous reactance, and it limits the short circuit current to a smaller value, because if the reactance is much larger, the current will be reduced. But it causes difficulty during the parallel operation of the machines owing to the smaller value of the synchronizing power. That is, when we try to operate two generators in parallel, which is quite common when we have got such a large power system being operated in integrity. So in that case, it becomes difficult for the machine to operate in the parallel condition. Larger the value of SCR increases the stability of the machine and improves its voltage regulation. Now when we have defined the phasors, there we have seen the angle del, and that angle del is the angle between the stator field and the rotor field, and if that del increases above the 90 degrees, in that case the pole will be slipped to the other pole pair, and that it is known as the out of step operation. So if the SCR is larger, that means that the stability of the machine will be better and it improves the voltage regulation, that is the drop under the loaded condition will be less. So the SCR of a high speed non-salient pole alternators will be lying between 0.5 to 0.75, whereas it lies between 1 to 1.5 for the low speed salient pole alternators, that is your hydro generators will be having an SCR of 1 to 1.5, and your turbo generators will have an SCR of 0.5 to 0.75. Therefore, salient pole alternators are more stable than the non-salient pole type of alternators. Now we'll come to the individual methods how to calculate the voltage regulation. So over here, for calculation of the voltage regulation, we'll have the plot. We'll have this plot of OCC and SCC, that is the open circuit characteristics and the short circuit characteristics, and we can have this at the same field current. We can have the value of the SCC and OCC, and we can say that E1 by I1 is equal to the synchronous impedance, that is the open circuit voltage by the short circuit current gives us the synchronous impedance. So the synchronous reactance will be equal to the under root of ZS square minus RA square. RA square is calculated with the help of the calculation of the measurement of the resistance of the armature circuit. So now here you can see the phasor diagram which had been drawn before also. So IA is because this is for the current is in phase, current is lagging the voltage by an angle phi. So your V cos phi plus IARA drop will give you the no load EMF, and your y axis is V sin phi and I axis. So you can calculate as E0 is equal to OB square plus BC square, and OB is nothing but OB is your this part, that is your V cos phi plus AB, that is IRA, and the y axis BC is your V sin phi plus IA axis. Not BC, it should be CD square. CD square, so it will be V sin phi plus IXS, and therefore your E0 will be under root of V cos phi plus IRA whole square plus V sin phi plus IXS whole square. So the percentage regulation is your E0 minus V by V. Now what is the drawback of this method is the value of regulation for unity power factor or leading power factor can also be found in a similar way, but this method is not accurate because the value of ZS so found is always more than the value under normal voltage conditions and saturations. Hence the value of regulation so obtained is always more than the actual test. Hence it is known as the pessimistic method. The value of ZS is not constant, but it varies with the saturation condition of the cores. So at low saturation levels, its value is larger, because then the effect of a given armature ampere turns is much more than at high saturation. And under short circuit conditions, saturation is very low because armature MMF is directly demagnetizing. Plus the value of ZS usually taken is that obtained from the full load current in the short circuit test. Here armature reactance XA has not been treated separately, but along with the leakage reactance only. It is the combined reactance, that is XS has been taken, not XL, and the armature reactance drop has been considered separately. So these were the disadvantages of the synchronous impedance method, and today we have discussed about the definition of the voltage regulation, then how we can determine the voltage regulation, measurement of the armature resistance, open circuit characteristics and short circuit characteristics, because these three are the basic requirement for calculating the voltage regulation. And today we have discussed one of the methods for calculating voltage regulation practically is the synchronous impedance method. So thank you.